Okay, so what we need to work on today is how irrational or complex roots of polynomials always come in conjugate pairs. So a plus bi and a minus bi, those are conjugate pairs of complex roots. And similarly, a plus b root c and a minus b root c are complex pairs of irrational roots. So let's see how this works. If I'm asked to find a third degree polynomial with roots at 3 and at 1 plus I know because it's third degree it needs to have 3 roots. I have 2 of them, but because one of them is a complex root, I know that the other root has to be 1 minus I. From there, I can say, well, factors of my polynomial, let's call it P of x, is x minus 3, that's because 3 is a polynomial, also x minus 1 plus I, because 1 plus I is a common polynomial, and the last one is x minus 1 minus I, which was not the given root of the polynomial, but I could infer it because 1 plus I was the root. So now I need to multiply this out. And when you multiply it out, you'll actually see why they have to come in pairs. First of all, let me distribute the negative in both of the complex factors. So x minus 1 plus I. And then I'm going to multiply these complex roots first. So I'll have x minus 3. Now it's a 3 term by 3 term, so this time I'm going to do it the long way. So 3, divide my rectangle into 3. That's x minus 1 minus I times x minus 1 plus I. And I'll get x times x is x squared minus x plus ix minus x plus 1 minus I minus ix plus I minus I squared. And then this great thing happens. This minus ix and minus plus ix cancel. The plus I and the minus I cancel. I squared I know is negative 1. So what's in this square really is the opposite of negative 1, which is positive 2. So this works out to x squared minus 2x plus 1 plus another 1. So it's x minus 3 times x squared minus 2x plus 2. And then I multiply these out, and again that's 2 terms by 3 terms. So I have x squared minus 2x plus 2 times x minus 3. And I'll have a cubic minus 2x squared plus 2x minus 3x squared plus 6x minus 6. So I have x cubed minus 5x squared plus 8x minus 6. And there's my polynomial.